here are the answers I've gotten yesterday. Finish these up.
Why does it say second class, not that?
Oh, I'll explain that later. No, I'm not saying it'll make sense, dude. All will be revealed. Those went pretty quick when you think about it. All right, first things first, let's take a look at our warm-up. All of this, applying these properties of definite integrals in these different ways. All of these are really helpful to help us understand and use these different properties. So as you check what you have, any of these that doesn't make sense, I'm happy to talk through. We can talk about whether it's the geometric stuff over there or it's just straight up applying the properties over here. If you have a question, let's talk about it. All right. Well, we've got a lot of little things to talk about here before we get into our lesson, which is really important. So first of all, we got to talk about finish off the college week stuff, and that's what this knows. So there's a question yesterday. It was what was my favorite class in college that was not a math class? I believe that was asked in here, and I didn't really have a good answer. Did I tell you about my walking class? Was that no? Okay, so I had a couple. I didn't actually like that class, but that was a class that wasn't a math class that I took, where you had to walk, and if you ran, then you didn't get an A for that day. Crazy times. But I think my favorite class that was not actually a math class, my senior year when I was doing, when you're doing like your for education stuff, you go spend time like in a school and you teach some lessons and stuff. And then once a week I had this class that was like, for some reason in my head, it was like a 4-hour afternoon like debrief after you've been at the school all day or something like that. It was a really long amount of time that you had to spend, but it was once a week. It was a once a week class. But I think that was probably my favorite one because there was only 4 people in there. It was 4 of us and the teacher, because there's only 4 people trying to get a degree in math with education certification at the same time. And one of those, so you had me, you had two other these two other girls that I spent most of my college taking the exact same classes because we wanted the same degree, and we were all somewhere between 21 and 23 years old at the time. And then we had this 60-year-old woman who was also trying to get the same degree, and it was a hilarious class. And we either did like, well, it was, you just kind of talked about what happened at, in your experiences or whatever. That was just a fun class. Anyways, so what I did after college, as soon as I graduated, I thought about pursuing throughout my senior year, I thought about pursuing my graduate degree first. I thought about going and getting a degree or a master's in statistics, because that was kind of thrown out there to me because I didn't really like my stat classes in college. But I then took the GRE and didn't really do very well on the GRE and said, I'll just go straight into teaching. So I went and taught at East Lawrence High School for a year, and that was horrible. Didn't like that. Did not plan on teaching a second year. That was not what I expected to do. Probably about by week 2 of that school year, I thought, well, I'm going to gut this out. I'm going to finish it, and then I'll go do something. I'll figure something out. I'll go change directions. But then somewhere around February of that year, Ms. Perkins called and said, hey, I'm starting a school. Would you like to come teach there? And that's why I've been at ACE ever since, because ACE opened, and I probably would not have taught a second year if I didn't get that opportunity, because I did trust Ms. Perkins. Remember, she was my principal in high school. And so I thought that was, it was a unique opportunity. I was excited to try it out. And it was, needless to say, a better experience than what I had at East Lawrence High School.
What made your experience that bad?
I was given many different classes. Like, as a teacher, the more different things you teach, the more time consuming it becomes to be ready for a school day. I was given lots of different ones of those. Lots of discipline problems, lots of very little help. Like a kid could cuss me out, right? And I would write them up, send them to the office, and but I teach them twice a day because they failed some other class. They're still trying to pass their sophomore math class and their junior math class at the same time. So they would then come back to me later in the day, even though they why are you sending this kid back to me? They would give them ISS for just that period. It's like, you're suspended, but just that period that you cuss the teacher out. I don't want to see this kid again. Stuff like that. Just weird stuff. Probably the best story is that kids would dip in class all the time, even though it was they were underage. They weren't even allowed to buy it at the time, but the school did nothing to try to prevent this, right? So as a teacher, you just kind of make you're like, well, I don't want them to do this, but apparently it's fine. So I at least don't want them spitting on my floor. So one kid was actively spitting his chew on my floor. So I'll write you up, send you to the office or whatever. And I guess he didn't want to get in trouble again. So he would come to class every day. He would take off his boot. And he would spit in his boot, put it back on, and walk out of class.
So they just bring a bottle like everyone else.
Or
just don't do it.
Just don't. Yeah. Anyways, yeah. Anyway, so that was the level which I was working with. I did have one student that worked really hard to make an A in my class. Because her mom said that if you make an A in geometry, you can drop out and get your GED. She made an A in geometry. I don't know what happened to her after that. She worked really hard though. And she designed what is now one of the tattoos on my arm. Yeah. She was the hope. Kanani Nixon, wherever you are. Good job.
What about your walking class?
My walking class? It was like Tuesdays and Thursdays at 6 p.m. You show up, you gotta be dressed out, you have to do a certain amount of laps around the track, you gotta walk, you make 100.
Why is that a thing?
You had to have 2 PE credits. I got a 1 hour credit for walking. I got a 1 hour credit for my first aid class, which I went to class 3 times as soon as I could prove that I could do CPR. Didn't have to come back. Anyways, I wanted to take, like they had like tennis and yoga, and honestly I wanted to take those, but they would always conflict with like something I had to take that semester. So I went with walking in the first day. Anyway, you do what you have to do to get your degree in the amount of time you want. All right, other thing we need to talk about today for sure, our calculus wedding is coming up. Many of you, most of you filled out a form that I threw out last night, which is essentially, it came down to voting for who is going to be our bride and groom representative at the calculus wedding. And not all of us voted, but basically with the votes that we have, and it was not unanimous by any means, but based on the votes we have, there is clearly that only one person can win for both. Kachi is going to be our groom, and Elizabeth is going to be our bride. So that is going to be our play those roles for next week. So if you're wondering, that's how it will work. And on Thursday of next week, again, we want to be dressed. We want to be looking pretty good. All right, we talked a little bit about that, guys. We want to look as nice. You know, I'm going to probably wear a suit. I'm going to be officiating as well, so that'll be fun. But we want to have some snackage and we got to have a reception afterwards. So be thinking about some snacks that you can bring. I'll try to bust into Kroger and get some snacks myself. But it is pretty important for us to have a good reception afterwards. And as I mentioned, if you do have first lunch, which will be right after the wedding, you're welcome to stick around and hang out in here and have lunch as well. Yes, sir.
So like, when we come dressed, do we come dressed like that, like to school, or do we change out?
You can do either.
Okay.
I will make sure that the teachers know. Or if you want to, I mean, I would probably just wear it. I mean, personally, I'm just gonna wear a suit that day. As little fun as that is.
What color is your suit?
It's like dark gray.
Okay, that's not what I was expecting.
Really?
No, I was expecting like purple plaid.
Purple plaid for me? No, I was
Saturday afternoon.
Saturday?
David S. Pumpkin
Yes.
suit. Oh my gosh.
Today?
No, I don't. I want it to be classier than that.
You're right.
The only reason I even have that suit is because I was in a wedding years ago. I had to get,
Okay.
Oh, I thought you were talking about the pumpkin suit.
No,
No,
Okay.
no, I was David S. Pumpkins for Halloween years ago, and I still got it. All right, so now that I think we're all on the same page, homework for the next week is just, we got a set of cons. Again, most of them are going to be practice and review of a lot of stuff we've done lately, so you don't have to wait until Thursday of next week. You can get that practice in. And a big thing is what we're talking about right here, right now. For the rest of class, we are going to start really investigating these weirder functions. We've been concentrating on these definite integrals, these functions that have very geometric, they have a lot of geometric qualities. We can calculate them with trapezoids and rectangles and triangles. But if we have a function that is all curvy like this, which is most functions, and we want to evaluate a definite integral, we know that it's not so clear. We can't just rely on geometry all the time. But what we're going to do today, and again, it seems like we're just dancing around this idea of getting and dealing with this, but this is again a very important piece of this class, is we are going to look at estimating the area under these curves. And if we want to estimate them, we have a few ways. We have a few ways that we can estimate them. And what we're going to be looking at today is estimating by something called Riemann sums. Ooh, that's a terrifying word right there, but it's not. All right, what we're talking about today, what we'll talk about on Monday, we'll keep this going. this is going to be one of those things that when it pops up on that AP exam for you, these are going to be probably your favorite problems. All right. Even the students that have the most difficulty in this AP calculus class tend to favor Riemann sums and dealing with these things. So let's look at a particular function we are going to concentrate around. And notice how this crazy thing is set up right here. We're going to concentrate around this quadratic right here on that interval from 1 to 5. So if I were to write this as a definite integral, it would be from 1 to 5 of x squared over 2 minus x plus 1 dx. And I'm going to go ahead and graph this. I'm going to use my calculator to just pull up a quick table. And plot some nice points. I've got a 0, 1, negative 1, 2.5. A negative 2, 5. A 1. Put in 1, I get out a half. Put in 2, I get out 1. And now it's pretty symmetrical from here. 5, I got out 8.5. 6, 7. Here's my quadratic. I'm also going to write out that table just so we can see those numbers, not just as points over there. Okay, so here is the idea, and just, now we've got this quadratic. Ignore the question itself for a second, because right now the question doesn't quite make any sense. We need to talk about what a Riemann sum actually is, and again, a Riemann sum is going to be used to estimate, to approximate this area, not exactly what it is. We are trying to get a better understanding of it. So, with this function right here, what a Riemann sum is going to do is it's going to estimate the area under this curve with a geometric shape that we do know a lot about. We are going to be using, looking for the word in the problem, it's not in there, we are using rectangles. When we hear Riemann sum, we are thinking rectangles. I'm going to try to estimate the area under this curve with rectangles. And I'm going to draw up here what a left Riemann sum looks like on that interval from 1 to 5. So what that means, if we're going from 1 to 5, in this 4 subintervals is saying that I want to use 4 rectangles. It's saying take that space, take that distance from 1 to 5 and split it up into 4 rectangles. And notice if I go from 1 to 5, it is pretty convenient that I've got 4 evenly spaced little intervals right there. Now, left Riemann sum. A Riemann sum is talking about rectangles. Left means that as I draw these rectangles, I am going to draw them to a height of where we touch an endpoint on the left. So in this first little section right there, again, I'm splitting that distance from 1 to 5 into 4 little rectangles. This first rectangle is going to go up until we hit a point on the left side of the rectangle. Left Riemann sum telling me that rectangle is going to go up. It's going to have a height that stops when the left side of that rectangle touches a point on the graph. The next one, the next rectangle right here, is going to go up a little bit higher, because notice how that left side of this rectangle is going to go up a little bit higher until it touches a point on the graph. The next rectangle, it's going to go up a little bit higher still until the left side of that rectangle touches a point on our graph. And finally, our fourth rectangle goes up even higher still. Left Riemann sum, 4 rectangles on this graph right here. Notice it's not perfect by any means. There's a lot of space left out. There's some area right there. There's some area we're not getting right there. There's some area right here. And there's a lot of area right here. And if I add together these 4 areas, and we'll do that in a second, is this going to be an overestimation or an underestimation? Under. We're missing out on some of that area. We know it's not perfect, but this is a way that we could use a shape that we know to at least get somewhat close. And we will have ways of using our Riemann sums and trying to get better and better estimations as well. But this is the general idea. So let's calculate this estimation. Our Riemann sum, our left Riemann sum for this over an interval from 1 to 5 for 4 rectangles. This rectangle right here has a width of 1, right? Because it's our base times height. The base is 1. The height, it goes up to the height right there when our x value is 1. It went up to a height of 0.5. We can see it on the graph. We can see it in our table as well. So that rectangle has an area of 0.5. My next rectangle has a width of 1 again. The height this time is 1. So this one has an area of 1. My third rectangle, we know that is significantly bigger. The width is still 1, but the height this time, right here at 3, my height is 2.5. So my area right there is 2.5. And finally, this largest rectangle, the width is 1 again. The height, 1, 2, 3, 4, 5. We can see the output at 4 was 5. And so this one has an area of 5. We put all these things together. 5 and 1 is 6, plus 3. And so our left Riemann sum gives us, I'm going to go left Riemann sum. Crazy abbreviation there. I got 9. Okay. So that was a lot of process of something that's going to become very familiar to us. You've seen the process for the first time. Thoughts, questions about anything that we just talked about? As we're looking at this, we said this is clearly an underestimation. It's not great. Any ideas on how we can make it a better estimation? What would you say, Kim?
We add triangles.
We can add triangles to it, which we will have a process that does something like that. So I do agree that could help. We'll talk about that a little bit later, probably Monday. But what about if we just keep it rectangles? Let's stay in the rectangle world. What could we do if we wanted to keep it rectangles?
Right Riemann sum.
So we'll talk about a right Riemann sum too. I think we're going to find that right Riemann sum isn't that much better, but we will talk about right Riemann sum as well. But what if we wanted to keep it a left Riemann sum? If we wanted to keep it a left Riemann sum, we wanted to keep it rectangles, what is something that maybe we could do to make it a better estimation? What do you think?
Like over, instead of like an underestimate, making it over. That means go up to like, where the right side of each, like rectangle touches the, or the function.
So that'll be a right Riemann sum, and we will look at that. But I think we're going to find, and we'll draw that in a second. I think we're going to find that that is just as bad, but in the opposite direction. Where this was vastly underestimated, I think the right Riemann sum we're going to see is vastly overestimated. But there is something we could possibly do. If we wanted to keep it rectangles, we wanted to keep it left Riemann sum. What do you think?
Should do it horizontally.
Horizontally? That's interesting. But that'll get kind of confusing. I think we could figure that out. We can do Riemann sums horizontally if we really want to. But unless we change something, it's still going to be a pretty off estimate. So what I'm thinking is we could adjust the number of rectangles that we're using. Notice if we were to change this, and I'll just erase everything we've done here. Instead of 4 rectangles, if we double it, or triple it even, let's say we're doing, it's going to be a lot. I'll just do 8, because I don't really feel like drawing out 12 rectangles. If we did 8 rectangles instead of 4, well, if we take this space from 1 to 5, and we cut that, that's a distance of 4, but we cut it into 8 rectangles, that means that we're going to draw a rectangle every half unit. Every half unit, that rectangle has to go up to where it touches the function. Again, it's just the left side of that rectangle going up. But notice, even if I just double the number of rectangles, again, it's still an underestimation. There's still stuff missing, but it's a better estimate of what we have. What would happen if we didn't just have 4, we didn't just have 8? What if we had an infinite number of rectangles?
Give you the right amount.
It would give us the perfect amount. If we had an infinite number of rectangles, 4 divided by infinity would be 0. So we would have basically every width right there would basically be 0. There'd be no space to leave any gaps. There'd be no space to leave area. So that's how we will lean to define a definite interval. We can define it with limits, but that's just thinking how this does help. So it doesn't have to be, again,